Yes, sir. Yes, sir.
Screens are rotating, right, sir?
Sir, you are audible, sir. Screens are so fine.
Yes, okay, sir.
Slides are moving.
Okay. Now we are discussing random forest. It is an ensemble approach, one of the ensemble approach. Many ensembling models are there. So now we'll discuss specifically on random forest. Ensemble learning means in provide of best to fit model, to provide a best to fit model for the given data set. The basic models, in some cases, the basic models may not provide a best model individually. Individually, the basic models are not able to provide a best fit model. For example, a one support vector machine or one decision tree, one logistic regression, one linear regression may not provide a best fit model. Either it may be getting underfitted or overfitted. So in that case, we can go for ensemble learning. Ensemble learning means we can combine these basic models to provide a big stronger model, to provide a big model so that it can provide a best fit model. That is how we are mixing them, either it is parallelly or sequentially, means training process. Which so we are mixing two or more model means which model should train first, which model second, which model third, or how much data we will allocate. That is a case that based on that the ensemble learning approaches are divided. So why we are going for ensemble learning means, so to provide a best fit model when a single model is not able to provide, when a single individual model is not able to provide best fit model, we are going for the mixing, we are grouping some models to provide a best fit model. That is an ensemble approach. Ensemble approach. So here ensemble is maybe a sequential process or it may be a parallel process. Sequentially we can train means two or more models are trained on a data set one by one. One model will be trained first, second model will be second, and third, like that. All data set we are using, all data set. What are the number of rows, columns, completely we are using for all the models. Understood? So that is a sequential approach, one after the other, one after the other. So if you are selecting three models, uh, first one model will be trained on, and the next model will be trained on that. Here, how it is going to be like, first we'll conduct a mid exam. First we'll conduct a mid exam for BTech students, let's say example. Out of 60, 30 members got above 15 marks. Out of 20, above 15. Right? They are passed, like let's take passed. Out of 60, 30 members are passed. Passed that subject out of 20. Next, remaining 30, we are conducting what? Extra mid. Not for all. 60 members first we have conducted. Out of 60, 30 members have passed. For the remaining 30, we are conducting makeup mid. For remaining 30, we are conducting makeup mid. Out of 30, 10, 15 people are passed, and for the 15 people, again one more makeup mid or summer semester, like that. So wherever we got error, or wherever we for which model is not able to classify correctly, which where data. So on that data only we are continuing process. Sequential process is continuous, one after the other. The example model is ADA boost. This is a boosting technique. Again, I will explain what do you mean by boosting, what is mean by bagging. This is a boosting technique, means sequential process. Here it will be sequential or it will be parallel. And one more thing, one more combination. Either you can combine two or more models, homogeneous or heterogeneous. Understood? Homogeneous means two decision trees or two SVMs or two logistic regressions. No problem. All are same models we are combining. That is homogeneous. Homogeneous ensemble learning. Homogeneous. How they are executing, either it may be sequential or it may be parallel. Next, one logistic regression, one SVM, or one SVM, any combination, one decision tree. How they are executing, either sequentially or parallelly. So like that, four different combinations we may have. Four different combinations. Four different combinations in ensemble learning based on the combinations, either combining two or more homogeneous models or heterogeneous models, and how you are executing them either sequentially or parallelly. Based upon this, we are grouping them, means they are making them four options. Ensemble learning models are four types. That four types are that like parallel execution. See, this is a sequence execution. Sequential means one after the other. This is a data set. This is the data set. Model 1 on the error the model 2 will be trained, and on the error the model 3 will be trained. So here 20% error, here whatever the error we got, here whatever the error we got, the average error will be the final error, or average accuracy will be the final accuracy. That is a sequential process. Sequential process will be executed on like a mid, otherwise summer, winter semester, summer semester, like that. Regular semester, some students are failed. Okay, we'll conduct a winter semester. For whom? Not for all. Regular semester will be conducted for all the people, and winter semester, those who are failed in regular semester, they will come to the winter semester. In winter semester, for example, 10 members are participated in winter semester and 5 members have passed, and remaining five members summer semester, like that. When wherever we got error, which data point is getting error, so that point only we are moving for the, that error is only carry forward, not the good option. So that is a sequential approach. And parallelly here, uh, all the models will be executed on same data set, same time. All models will be executed on same data, same time. Okay, the result of, for example, model 1 result, model 2 result, model 3 result, the results we are combining. That is a parallel process. Here in parallel process, we can divide the data set or we can't divide the data set. For example, 3 rows are there, 100 rows, 3 columns are there. In parallel processing, parallel ensemble learning, model 1 will be trained on 3 columns, but 50 rows it will take. Model 2, model 2, 2 columns, 50 rows, any 50 rows randomly. And model 3, like that, we are either we may split or we may not split the data set. Then how we can provide the result, we'll discuss. If it is a regression, model 1 output, model 2 output, model 3 output. If it is regression, average of this. If it is classification, majority of this. This is saying yes, yes, no. So final output is yes, like that. This is a parallel execution. Sequential and parallel execution. And how we are combining homogeneously or heterogeneously. Homogeneous means same models are taken. Heterogeneous means the different models. One SVM, one decision tree, one logistic regression, heterogeneous. And how they are executing, parallel or sequential. How we are combining that. That is a heterogeneous or homogeneous combinations. Yeah, here four combinations, either bagging models, boosting models, or bucket of models, and stacking. So here in bagging concept, the random forest will come. In bagging concept only, random forest will come. So it is, what is a bagging models? Bagging model means parallel execution and homogeneous combination, that is a bagging. And boosting, homogeneous, but sequential execution, that like that. Okay. Now stacking is completely these two are heterogeneous, these two are heterogeneous, and this is heterogeneous sequential, this is heterogeneous parallel. Bucket of models. So parallel execution, all models are executed at once. Homogeneous model we are selecting, all models are same, executed at once, that is a bagging model, bagging. And homogeneous model, same model we are using, and two SVMs, two decision trees, two logistic regression, same models, but they are executing sequentially, one by one, not at once. That is a boosting concept. Boosting concept. Bucket of model means heterogeneous models. 3 and 4 are heterogeneous, means one SVM, one.
Sir, your voice is not clear.
My voice is not clear. Okay, I will come again. Now is it clear? Now is it clear? I'm not getting.
Yes, yes, sir, it is clear.
Okay. So
Yes,
ensemble learning, we are mixing two or more basic models, So how we are mixing, homogeneously or heterogeneously? Okay. After mixing, how you are executing, how you are training on a data. How you are training on a data means the two or more models will be executed at once, parallel execution. Two or more models are execution one by one, sequential process. Okay, based upon these combinations and model selection, we can divide ensemble models are four types: bagging models, boosting models, bucket of models, and stacking of models. The bagging means homogeneous models. Homogeneous means same models will be there. Two logistic regression, or two decision trees, or three decision trees, or 10 SVMs, 10 decision trees, like same models we are taking. That is a homogeneous. And execution is parallelly. Execution is parallel. Execution is parallel. All models will be executed at once without depending on each other, or are independent models. Okay, 100 decision trees you can take, 100 SVMs you can take, no problem, but no link between, no connection between these models. Every model is independent, they are providing independent results. Let them train the model and let them provide the result, that's it. Don't connect them. That is a bagging process. In boosting, same homogeneous, same models we are combining, but they are executing sequentially. Three SVMs we are selecting, or 10 decision trees we are selecting, but the execution process or training process will be one after the other. One model will be trained at once, means they are not independent, they are dependent. First model will be trained, and second model will be trained on leftover of first model. Third model will be trained on leftover of second model, like that. Okay, these are the boosting models. Example models are like AdaBoost, adaptive boosting method, gradient boosting method, extreme gradient boosting method. This is very powerful. So if your data set is not able to handle with ensemble learning now, then we should go for deep learning models, neural networks, ANN, CNN, RNN type. So if the data set means, if XGBoost, AdaBoost, or GBoost are not able to solve, not able to provide a best fit model, then this is final task. We should move on to deep learning. And Bagging example is random forest. Bagging example is random forest. So homogeneous models, parallelly they will be executed. And bucket of model, these two are heterogeneous. Different two models we are taking. One logistic regression, two decision trees. Like that, any two decision trees, two SVMs, or one decision tree, one SVM. Like that, mixing of different models. Okay, how they are executed? How they are executed? If it is parallel, bucket of models. If it is sequence, it is a uh, heterogeneous sequential execution. It is stacking of the model. Push stacking operations, push and pop. So like that, we are going to push all the models to bind the uh, big ensemble model, that is called as stacking. Heterogeneous sequential execution. Bucket of models is heterogeneous parallel execution. I hope you understood these combinations. Next, four combinations are completed. How we can so we can say ensemble models are supervised learning models itself. They are not unsupervised learning, they are supervised learning models only. So they can do regression and classification as well. They can do regression and classification, right? Ensemble learning either is boosting or bagging models or stacking or bucket of models, anything they can be do regression, they can do classification also. How classification is done, we'll see. For example, this is the data set. Okay, this is ensemble learning. So and parallel execution, sorry, parallel execution, parallel execution. Next, this data set is divided into small number of pieces, like respectable pieces. Data set one is not from anywhere, this is from the main data set only. 2 3 4. So we are doing, for example, 5 columns, 1,000 rows are there. 5 columns, 1,000 rows. Here we are just taking only 3 columns and 500 rows. Here 5 columns, 500 rows, 2 columns, 500 rows, and 3 columns, 100 rows. Like that, we can divide our own wish. We can divide the data into any parts, any number of parts, and uh, train the model. Model 1, model 2, model 3, and model 4. For example, model 1 has given the result as class 1. This has given class 2. This one will be class 3. Like that, it will be trained. So majority we are taking. For example, here we got yes. Yes. This is the output is no. Here the output is no. Sorry, yes. Then majority is yes. So we are going with yes. For example, 10 people I am asking, 10 persons. Individually, I'm asking 10 persons, one by one. 10 person one, whether to watch. What is your opinion on Devara movie? Second person, what is your opinion on Devara movie? Whether to watch it or not. So 10% I am asking, 10 persons. So what is their outcome? What is their results? Out of 10 persons, 8 persons said yes. 2 persons said no. So majority people said yes now. So my opinion is, my own opinion is to final result is yes. That is the ensemble approach. How they are saying, for say, for example, person one answer is yes. Person one uh, only taken the features as a comedy. Based on the comedy, he said yes. Person two, based on some lengthy scene, he said no. Person three, based on the fightings, based on the crime, they said yes. So these 10 people are worked on, watched same movie, but they worked, they have taken their own decision based on different features, different features. So my task is to just combine all the decisions and take the majority for classification. This is the ensemble approach of classification. Okay, any doubts you can ask. No problem. Yeah, bagging, homogeneous parallel model will be executed. Parallelly they will execute it. Said boosting also homogeneous, sequentially, one by one they will be executed. So this is a bagging approach. Data set is divided into parts. First, then this is the model one. Let's say logistic regression, logistic regression 1, logistic regression 2, logistic regression 3. Now it will work on this data set, it will provide its result. It work on its result, this will result. It will work on its data and provide the result. This is a bagging approach, means these models are independent, not depending or not waiting for anything. They have their own data set and they will be trained on it. But come to the boosting, first complete data set is provided to the first model. Then whatever the leftover parts like error or any defaults will be passed to the second model, and second model will be trained on that over part, leftover part only. And the same way, second model will be leave some leftover part like error. The third model will be, or here this model will give the output, this model, second model also will give the output, third model also will give the output. The final output will be based on weightage. First model output is a fifth, yes, second model output is no, third model output is no, but for this it is 20% weightage, second third model is 10% weightage, first model weightage is 7%, 70%, because this is the first model, it is going to trained on big data, complete data, but the second model is trained on how much leftover data it is there, and third model is also. So the weightage is given for the output. Here in bagging approach, no weightage, all are equally participated, each and every decision is equally weighted, equal weightage means all are equal, parallel execution. But in sequential execution we are giving weightage to each and every answer. So 70% yes, 30% no. So we can directly say yes here. That is the way we can decide the output in boosting and bagging models. Some are the differences between bagging approaches to boosting approaches. Bagging will decrease the variance bagging will decrease the variance. Here variance is nothing but distribution of data. If the data distributed uh, uh, randomly is also good, but distributed very separately. For example, x values are there, x values 1 2 100 101, like that. So this is has a high variance data, means all the numbers are in going in a some frequency, some numbers are will go another frequency. If I am asking temperature, body temperature, if I am going to collect body temperature, so okay, you all said my body temperature is 95, 100, 102, something like 105. Okay, this is a good variance, but somebody said 0. This is a biased one. Means this will provide a high variance. Somebody says 1000. So this data is not fit into this data, actual data. The 0 and 1000 will not be fit into the body temperature. So in that cases, high variance data, that is called high variance data. So when you have this type of data, the bagging approach can decrease it, can provide good best fit model. And not bias. Bias means average of predicted. This is a target variable y. So you are not going to you're always predicting here only your y predicted values here. The difference between y value minus average of y predicted values will be the bias. That is, variance is data set and bias will be said in the model. Okay, so what we can say, if we are using bagging approach, we can overcome variance, but we can't provide good bias. Okay, but boosting can decrease the bias, not variance. Understood. In bagging, each model receives equal weightage, so no proper weightage is given. All are equal. All answers, all outputs are equal. But in boosting, The model weightage is based on their performance, how much confidence they are giving in approach. In bagging, all the models will be executed independently, but in boosting, it is a sequential process, so they are depending on each other. Second model is depending on first model is depending uh, trained on complete data sets. Okay, in bagging the training data is splitted into small number of parts, small data sets. In boosting, every new subset comprise all the elements. In boosting, there is no separation of data set. Only error or misclassified data is provided for the next step. Hence, that is not a type of splitting. But in bagging, initially we are just cutting the data into small number of pieces and we are assigning each piece to each one model. That is these are the small differences between bagging and boosting. Here we need to uh, give importance to which one is doing what. Bagging can decrease the variance, boosting can decrease the bias. The variance is uh, problem at data, distribution of data. Variance is high means variance is low, the distribution of data is good. Variance is high means the distribution of data is not good, not relevant. The distribution of data is not relevant. Some data is like 1 2 3 4 5 6 7 8 9. The frequency is good, but suddenly if we get unfrequent data, so that is, then we can say it is a high variance data. Then bias means capability of the data, capacity of the model, not data, capacity of the model. Bias will say uh, model capacity. Variance will concentrate on data set. Variance is high means data set is not good. Variance is low means data set good. Data set is good. So bagging model can handle when there is a high variance data, though the bagging models can easily handle that. But bias means it is relevant to the model. It is relevant to the model capacity. How much strong, how much capable the model is. Model capacity. So that boosting can overcome that high biased one. It can be reduced. Understood? So boosting can reduce bias and bagging can reduce variance. These are the two important differences. So here now come to the random forest. It is a bagging approach. Bagging approach. So it means homogeneous models we are combining. Homogeneous means same models we are using, like 10 decision trees, 10 SVMs, or 20 decision trees, like that. Same models we are using, we are combining, and how they are executed. How they are executed? Parallelly, not sequentially. Parallel execution. All or how many models you selected? For example, 10 homogeneous models you selected. All 10 models executed or trained independently. They have their own data set. Their own data set means one big data set we are distributing to uh, each and every model. Small part of data is given to some data. So parallel execution, not depending on any other. All the models will be trained at once. This is the random forest, is one of the ensemble learning model. Okay, if they are executed parallelly, how we can find out the output? Which model output which we can consider? For that case, before that, random forest is same like decision tree or else it can do regression, it can do classification. Random forest can do regression, can do classification models. Here, for example, here random forest, I'm going to take three decision trees. Tree 1, tree 2, tree 3. I have built, right? Now this is executed on, this is a target variable x1 and x2. This is a target variable x3 and x4. This is a target variable. It may have x1, x2, or x3. Anyway, we can split the data. Anyway, split the data. It is not like training and testing split. This is just random split. Random split. In training and testing, we are just going to split the rows only. Random rows we are splitting. 70% have data or 80% have data for training and remaining for testing. And that way we split. But here, columns also, features also we are splitting. Features and rows. Now, tree 1, tree 2 and tree 3 will be builded and the output is given. Tree 1 is given as red, tree 2 green, tree 3 is red again. So output is majority is the output in classification task. Majority of the result will be taken as the out of 3 2 red. That's why the final output will be the red. So that is a classification. For example, if it is a regression task, this 3 predicted 20, this 3 predicted 30, and this one predicted as 40. Now the final output will be 20 plus 30 plus 40 means 70. 90 by 3 average of the output. Average of all the output will be the final ensemble model output, random forest output. That is 30 is the output. In case of regression, in case of classification, majority will take. In case of regression, average will take. So how it going to be applied here? N number of samples, m number of features. This is our data set. Distribute like this. Features means columns and rows. Now we are dividing some columns and some rows like this. So with replacement we are dividing means some data may be common here, and here also it will be present like that. First task is to split the data. How many models you want? For example, I want to train 10 models or I want to train 100 models bagging. Understood? So if you want to train 100 models means divide the data set into 100 parts. If you want to train 10 models means divide the data set into 10 models. Like that, after splitting the data, then train a model. Random forest means is blindly trained on a decision tree. Decision tree is fixed for random forest. So it will be built on decision tree. First data set First data set, decision tree is built and it will give some output. And second data set, this will be built, and third data set is output is this one. Okay. If it is classification, take the majority output. No weightage is given. All are given equal priority. All the models, all the trees will be given equal priority. That is a random forest classifier. If it is a regression, for example, this is a regression data. X1, X2, X3, X4 house price prediction dataset, X1 dataset, and this is a target variable we are going to predict. For this also same, we are going to split the data. How many? For example, I want to train 5 decision trees. So first step is to split the data into 5 parts. How many? 5 parts. 5 parts. So you can, in part 1 you can take 2 columns and some rows, no problem. Part 2 you can take all columns, all rows maybe. And part 3 is only x3, x4 and just some rows, no problem. Not linearly, more randomly we are going to split. Okay, this one, this one, this one, anyway we can take. That is a random split, any number of parts. Then now after splitting the data, now assign a model. It is a bagging approach, so homogeneous models. 5 decision trees we have selected. So each 5 decision trees will be trained on 5 parts of the data. 5 decision trees will be trained on 5 parts of the data. Understood? Next, tree 1 output is 3000, tree 2 output is 2000, so 2,90,000. Tree 3 is this one. So final output is average of 3 outputs is the final output. That is the prediction out of regression model. If it is classification, majority we should take. If it is a regression average we should take. This is the random forest approach. Same. How we can build a decision tree. Same process. You can first you should calculate the entropy of target variable, entropy of each and every column with respect to the target variable. Then calculate the information Guinea. So which column has the highest information Guinea, that column will be selected as a root node. This is a common procedure. Procedure of model training process is will not change. But how we are combining the model, how we are executing the model, which data we are providing the model, we are providing to the model is different. In bagging, example is random forest, homogeneous models we are going to train. Parallelly, they will be executed. First step is to split the data into number of plots, number of parts. Then for each part, train a model. For example, part 1, decision tree. Part 2, decision tree. So homogeneous now, how many number of parts? All the parts will be trained on same type of model. Then how we can take the output? If it is a regression, average of all the models will be the final output. Or if it is a classification, majority of the output is the final output for the classification model. So this is the random forest example. Random forest. Yeah. Any doubts you can ask. So if you don't have any doubts, then we'll move on to the execution part. Hello.
Sir, continue, sir.
Sure. So we'll move on to the execution, sir. I will show the decision tree and random forest execution on Google Colab. So I'm taking the sample data sets from the Google Colab. So California house price prediction, train data is there. MNIST train data is there. This California house price prediction is a regression model, and MNIST is for classification. So on these two, one regression, one classification, I will implement two models, random forest and decision tree. First, we'll go with the decision tree. Just look at. So I'm taking pandas to read the data set. So now I'm reading the data set into a variable called d, pd dot read underscore, both are CSV files. So take the copy of this, read CSV. Just check the data if it has been copied into variable called d or not. Now we got the data into a variable called d. So these are the features. Longitude, latitude. Sir, is my screen is shared?
Yes, sir, it's fine.
House made in age and total number of rooms, and population, household, made in income, house value we are going to take as a target variable. This is our target variable, and the target variable values are these continuous values, not repeated values, continuous values. So it is a regression problem. Total number of columns are, sorry, rows are 16,199. So total it is 70,000 rows. 1, 2, 3, 4, 5, 6, 7, 8 columns are there. Just will describe the data. Yeah. So totally 20,000 rows, so 17,000 rows, and data type of each column is float. No, so no need to worry about all the data. All the columns are in a float data type. So it is clearly we can do any mathematics on this. So if it is string or object, then we need to worry about converting process. This is our overview of data. Now we are checking for any null values are there. Is there any null values? So I'm getting all false. Let's count any true. Yeah, 17,000, 70,000, all are false. So we can say that there are no null values in this data set. Next, I'm taking the target variable separately into a variable called y. D. This is my target variable. Now this is my target variable, and I accept that I'm taking all the features into variable called x, all the features into variable, and without a target variable, all features. So I'm dropping the target variable. Remaining will be into x. Now print x. Yeah, except the house value, all the columns are in all the columns and all the values are in x. We'll just find out the shape of the data. So total 8 columns are there, 70,000 rows. Now I'm splitting this data, x data and y data, into x train and y train. X train data, y train data. X test data, y test data. For that, using a library, so 4 parts. First, given data set, I have taken into target and features. First divided into 2 parts. One is target, remaining all are comes under features. Next, the 2 parts are divided into 4 parts. Training, testing, x train, x test, y train, y test. Same, train underscore test underscore split. What I want to split the data, x comma y, and test size is 20 percentage. Random underscore 20 is 20. X train. So we splitted the data randomly. X train data. Totally 13,600 for training. Now all are correctly divided. 13,600, 8 columns into X train data. 13,600 in Y train. This is a X train, Y train data, X test, Y test data. Now after splitting, we will going to train the decision tree model. That model is in sklearn dot tree. Import decision tree. It is a regression model, so regression data, so regression. Now dt is the model name, decision tree regression. Now just fit model is equal to dt dot fit xtrain ytrain data. So model is fit. Now we'll find out the error. So why should we? It is a regression model, so we need to calculate the error of that model. So from sklearn, import mean square error. I will calculate mean absolute error and mean square error. We can R square also we can calculate. So first y predicted values I will find. By giving x test data. Now print mean square error between y test data to y predicted data. This is a mean square error, mean absolute error. Y test data to y predicted data. So mean absolute error is almost 43,000. Very, very worst case, very worst thing. It's a decision tree model. Any doubts in this? This is a regression type of thing. Now same on decision tree, we'll try a classification data. MNIST tree. dd pd dot read underscore csv. This MNIST data, this is for handwritten digit recognition. So how many zeros, ones, percentage. So here the target variable is 6. So target variable is 6. Name not 6. The target variable name is 6. This will represent, all are representing a matrix, converted matrix. 785 columns means it is a matrix of flattened matrix. 785 means one dimensional array of 785. That will represent whether it is 1 or 2 or 3 or 4 or 5 like that, up to 9. When 100 digits are 0 to 9 only. So that's why here the number of classes are 0 to 9. Totally almost 20,000 rows are there. Just 20,000 rows are there. Now same procedure, find out the target variable into y. Remaining features are into x. So after removing 6, everything will be in x. Now once we'll check print of x, except the target variable remaining all in it, x. Next, after finding that, let's check the any null values are there. dd dot count the null values. Sorry, count the other than null values. So all are there are no null values in this. That's fine. So everything is good. Now same, split the data into x train, y train, x split, y x test to y test. X train, x test, y train, y test. This time I'll take 0.3 as a testing data. remaining 70% as a training data. Random underscore state 25. Now the data is splitted into training and testing. Test shape and train shape. Very huge number of samples are there for training and as well as for testing. Now after that, I'm going to train decision tree classifier for this. For this sklearn dot tree module only it is there. Import decision tree classifier. There in the first we imported decision tree regression, here decision tree classifier, and create an object like DC is our object for decision tree classifier. With that object we can fit the model. Now model 1 is equal to DC dot fit meanwhile yeah, it is fitted. Now find out the y predicted values. Yp is equal to model 1 dot predict x test data. I'm giving x test data, so that we will get y predicted. Now we have y predicted values. Print the y predicted values. All are repeated over 0 to 9. Now for classification, we are not going to calculate any error, but for this we will calculate accuracy, classification report, and confusion matrix will calculate. So for that, from sklearn dot matrix import accuracy underscore score, classification report, and confusion matrix. These three we are going to find out. Now we'll print accuracy underscore score between y predicted values to y test data. Accuracy is 83%. Next we'll print classification report. Same y predicted to y test data. So here we'll get all precision, recall, F1 score, and support count of each. So in that also accuracy also is mentioned. 0.83, precision of 0. How many zeros are predicted? How many correctly predicted? That is a precision. And recall on. Next, confusion matrix I will print confusion matrix between y predicted to y test. Yeah, this is a confusion matrix. Over here something problem. Not a good one, but a better one. Not a better one, but it is good. Not these upper diagonal and lower diagonal values must be low for this confusion matrix, but here some parts of the lower triangle and upper triangle will be some values. This is, so we can decorate it. Any doubts in this you can ask. This is a confusion matrix. The numbers are not look, but based on color. Yeah. So for classification and regression, both models on decision tree we have completed. Any doubts on this one? Shall I continue for the next random forest?
Yes, sir.
So here approach is same. If it is a regression, same. That take the data set, find out any null values, any high variance, low variance data, outlier, any problem in the data set, clean it. Okay. Then after cleaning the data, find out the target variable and split the data for training and testing. X test, X train, Y test. This is a common procedure. Now select the model. Now we are going to do random forest random forest model. So where that model is, then same. If it is a regression, calculate the error or mean squared error or R square error, mean absolute error or root mean square error. We'll calculate. If it is a classification model, accuracy, precision, recall, ROC. So these things we are going to calculate. But model only changed, result analysis same, and before the model selection is also same. Now same. California house price prediction train data I'm taking, same. Here it is D PD dot read. We'll go with random forest regression. Yeah, here it is. Decision tree classification. Again, I'm taking D variable PD dot read underscore CSV. Set house price prediction data. Check for the null values. Longitude, latitude, median age, total rooms, total bedrooms, population, household, median income, and median house value. Here the task is find out the target variable, which is a correct target variable that we should identify. And second is, are there any null values? Are there any outliers? Okay. What is the normalize the data, normalization, reduce the domination. These things we need to do before going to do selecting a model and training a model. So directly finding the target variable, that is into Y. Target variable is made in house value, and features are except that MEA.
Underscore value, sir.
Yes. Yeah, now once check the print X, print Y values. Same. Now find train test splitting X underscore train, X underscore test, Y underscore train, Y underscore test data. X comma Y. Test underscore size is 0. Novel type. State is 20. Now X train, Y train values we got. X to tested up. This is for checking whether it is correctly divided or not. If you don't have proper distribution, like same number of rows, same number of columns, if we get na, we may get error. Y test, Y train, X test, X train we have chain, and Y test only we should check. Yeah. Train data 11,900, test data 5,100 rows, X train 8 columns. Now after splitting, selecting a model, so I'm selecting from sklearn dot. These are all ensemble models. Random forest is ensemble. So sklearn dot ensemble import random forest regression. Same. RR random forest regression. Random forest regression. Here we should give, here it is mentioning number of estimators, means uh, number of uh, trees you want to train, number of trees you want to take. I want to take only 50 trees, means uh, uh, 50 individual models I want to train, and combination of 50 model results will be I am going to take average of 50 models. That is a important option here. How many number of trees, how many steps splits you want to do. Next, model is equal to r dot fit random forest model fit X train comma Y train. Now from here again it is same what you want to, how you measure the metrics, whether you want to calculate R square, mean square, or mean absolute error, that we can calculate. Here I'm calculating Y predicted value. Model name is dot predict. So X test values we are giving to get Y predicted values. Now calculate print mean squared error. Not importing because already I have imported that value. Mean absolute error in between Y predicted values to Y test data. Somewhat it is reduced. Print mean squared error in between YP comma Y test. Yeah, we can look at same data set we have used, but for random forest 32,000 as absolute error. Here 43,000 as a mean absolute error, but testing size also we are influenced. Here testing size is 0.2. Well, we'll change the test. We'll take same testing size. Take same testing size 0.2. Now we'll check which model is providing good. Same number of samples we are taking for training, and same number of samples we are taking for testing. Now, which one is providing good results, that will check. Yeah, 32,198 means when compared to the decision tree, random forest has reduced the 10,000 error, 10,000 value error it is reduced. There we got 43,000, it is reduced to 32,000. So performing better. So this is random forest regression model. Next we'll see random forest. Random forest classification. So from first we'll take the data. pd dot read underscore csv, same MNIST train data we are using. Again select the target variable y is equal to x values we have taken into all features into x. Just print the x. Yeah, except to sixth column, right? Sixth named column, we have everything into x variable. Same now again split into x train data, x test data, y train, y test, x train, x test, y train, y test. Train underscore test underscore split, same x values, y values. Here x values and y values I'm using from the beginning, but updated values it will take every time. No need to worry. So here in previous model, previous decision tree also I have taken x and y. In regression also I have taken x and y. Classification also I have taken x and y. But every time updated values it will take. Test underscore size 3 and random underscore state. So after splitting the data into training and testing, just train the model from sklearn dot ensemble models import random forest classifier RC random forest classifiers number of estimators. This time I'll took 100. So 100 trees I am going to train. Next mm2 is equal to RC dot fit extrain. This RC is an object. That object we are calling a method called fit by passing train data. So MM2 is the trained model. MM2 is a name that is a trained model that we can use for deploying and saving the model. For further purpose, a trained model RC is a just object. Otherwise, we can also create directly here with a class name we can call rc.fit xtrain comma ytrain. This will be trained and trained model will be stored in MM2. Now same y predicted values will find out mm2 dot predict from xtest. Now we'll print accuracy y predicted between y test values. This accuracy underscore score I have already imported. That's why I'm not importing again. Next classification report between y predicted values to y test data. This time the accuracy is improved, I think, from last to decision tree accuracy to, with the decision tree we got 83% accuracy, but with the random forest we got 95 accuracy. Now we'll print the confusion matrix. Matrix between y predicted values to y test data. Yeah. This time the upper diagonal values and lower diagonal values has been reduced. Now same test size will give and we'll test it. Here it is 0.3. Here also we took 0.3. Same amount of data we have trained both for decision tree and random forest, but random forest is performing little bit some better than the decision tree classifier. So we can say with the precision recall also, the not only the accuracy, precision recall also consistently performed. With this we can say the model is not getting overfitted or underfitted, not getting overfitted. Yes, any doubts you can ask now. Am I audible? Yes. Am I audible? You can ask any doubts.
No, sir.
So decision tree and random forest with implementation I have done. Sir? So I hope Sir said already how to import our own data sets to Google Colab and how to take the model. Otherwise, you can ask any doubts in this regard. Any machine learning or deep learning related, any doubts.